All right, these are the video solutions for homework 38 for calculus. So this is a handout that was provided through Haiku, and there are multiple pages to it, but let's start with number 1. So number 1, we are given a graph of f prime of x. So this is a graph of f prime of x. So please don't forget, as we just said twice, this is a graph of f prime of x. So I'm going to make sure that I know that. I'm going to label it. So in the same system, let's sketch a possible graph of the function and of the second derivative of this function. And we want to make sure we label those. So we're given a bunch of points that exist for the function. If you notice, there's no primes here. So these are all the functions. So I'm going to go ahead and take my blue, and I'm going to just start by marking all of these points. Now all of these points are part of the function. So I have f of negative 6, 0, and 5, which are 0. So that's a point here, here, and here. And then f of negative 2 is a positive 4, and f of 2 is a negative 3. So I have all of these points. The question is, how are they connected? So just like we did in class, I'm actually going to start by going through this and talking about f double prime. So what I'm thinking of here when I'm talking about f double prime is I'm looking at the slope of my f prime of x function. So I'm going to talk about the slope of this red line. So if I look at the slope, for this entire section on the left, it is a negative slope, and that negative slope is decreasing. Then once I get here, I have a really weird situation. So this right here is what we call a cusp. You might have seen one of these before. And so it's kind of undefined. Your slope is undefined at this location because you can't really say it's 0, even though it looks like it kind of curves. It actually just kind of meets at a point. So it's undefined slope at this location. Then on the right-hand side, we have a positive slope. It starts very positive, but as we move to the right, it actually decreases as well. So how does this translate to an actual graph? Well, I want to have a graph of my second derivative that is negative and it is decreasing. So I start negative, and so I can estimate here. The slope here is about, let's say maybe negative 1/2 or negative 1/3, something like that. So I'll start about right here, and I will decrease from this point up until the point where it is undefined. So I'm going to go down, and it's kind of like a vertical asymptote. That's not quite as down as I wanted to go. There we go. Let's try this again, one more time. So we have something kind of like a vertical asymptote, and it's undefined at the y-axis. And then on the other side of the y-axis, we have a very positive slope that decreases over time. So we have something that kind of looks like this. So you have something that's kind of hyperbolic when we're talking about the second derivative. So just in case you've forgotten, this purple is the second derivative of the function. So that's f double prime of x. Now I'm going to go into my blue function, since I've given all of this, and look at every piece of information that I can get from the slope and from the second derivative. So first I'll look at the slope of the actual function. And so I look at the first derivative to talk about slope. So at this location, I have the first derivative equal to 0. And so at that location, my slope is 0. The same is true over here. The slope at, not quite, at this location is 0, because that is where my first derivative is equal to 0. Right here in the middle, it looks like it's negative 4. So my slope is negative 4 at this exact location. And then it is positive, but decreasing. And then negative and decreasing. Here it is negative but increasing, right? So because I'm going more and more positive. And here it is positive and increasing as well. So why do we need the increasing and decreasing? Well, we can actually just look at our second derivative here to kind of link that together. To the left of the vertical axis, I have a decreasing slope. I also see that my second derivative is negative this entire time. Well, what does that matter? That means that my function is concave down for this entire range of values. On the right-hand side, my second derivative is positive, which means my function is concave up, right? I see that my slope is increasing. So how does this translate? Well, for the entire portion here to the left of -6, I have a positive slope, and that positive slope is decreasing, concave down. So it's positive, but it's concave down. So positive slope that is concave down. So what does that look like? Well, it looks like something like this. And then it's still concave down and increasing up until here, where it's 0. And let me try this one more time. So I'm going to go up to this point. Then it is still increasing, concave down, and then it's 0 right here. And then it goes down into this point, right? So it goes through 0, then all of a sudden has a negative slope. So in the middle, what happens? Well, it goes concave down to about a -4 at this exact location. Then all of a sudden it switches to concave up. So we're concave up, concave up, concave up. And then at this exact location, it is a slope of 0, so it's horizontal. And then I continue concave up, concave up, concave up. Let me try this again. Concave up to this point, and then I'm still positive slope, and concave up, so I just continue up like this. So there is my function, and these are all of the bits of information that went into graphing it. All right, for question 2, we're given a graph of f prime of x, and we're given some points for the function and the second derivative of the function. And we want to sketch the graphs of the function and the second derivative. So this right here, we're going to go ahead and label as f of x, just to make sure that we are unambiguous about it. And the first step I'm going to take is I'm going to look at f double prime of x. And the way I'm going to do that is I'm going to take my f of x, which is this red here, and I'm going to look at the slope of the red function. The reason I'm doing that, I'm sorry, this should be f prime of x. It's not very obvious there. And that's because the second derivative is just the derivative of the first derivative. So what I can do is I can look at the slope of this, and let's start by saying, okay, right here along this line is an interesting point because the slope is 0 right here. The slope also appears to be 0 about right here. And again right here at x equals 2. So these are my 3 points where it's 0. Now, the slope of this graph to the left of -1 is positive, and the slope of the graph just to the right of that is also positive. Positive for this section, negative for this section, and then positive here. Now the last part is we're going to look at how this is increasing or decreasing. So the first part is it's a positive slope, but that positive slope is decreasing. Here, this is a positive slope, but it's increasing. It is becoming more positive. Then right here at x equals 0, it switches from being an increasing positive slope to a decreasing positive slope. Then, once we go through a 0 slope again, we start to be negative, so we are increasingly negative. So this is kind of weird, but we're going to say that this is negative and decreasing. And then at a point of inflection right here in the middle, we switch from being negative slope and decreasing to negative slope and increasing because it curves up. So here I mean literally decreasing or increasing, including positives and negatives. And then finally we have a positive slope that increases only. So to actually sketch this, I'm going to go ahead and start with my points. So I have 2 points. F double prime of 0 is equal to 2, and f double prime of 1.5 is equal to -3. So I'm going to assume that's where this inflection point is. So that is equal to -3. So in order to sketch this second derivative, we want to take a really close look at these values. So my f double prime, which is the slope of f prime of x, is positive but decreasing. So this is positive and decreasing all the way down to 0. And then it stays positive and begins to increase. So it's going to go through this point. And at this point, it starts to become positive but decreasing. So what does that look like? Well, I'm going to go up through this point and then switch to that. And so, actually, let me back up for a second. So what I need to do is I need to be positive value, and I need to go like this, and then it's still a positive value, but it's decreasing. So I go through 0 right here. Now I become a negative value, and I'm decreasing. And then I go through this 3 down here, and now I'm negative but increasing through the 0 right there, and then I'm just increasing all the way up. So this is pretty much what our second derivative will look like. Now, for an actual function, we're going to go and look at a couple different things. So first we're going to look at the slope of f of x. So the slope of f of x is coming from the values of the red function. So up until this point, our slope is negative because f prime of x is negative. At the next segment, we have a positive slope. Here we have still positive. For this part, we have positive as well. Here we have a 0, and then we have positive slope again. Now, why did I add all these extra segments? Well, that's because the next portion is I look at the second derivative that I already sketched, and I can decide whether or not I am concave up or concave down. So, because my second derivative is positive here, this is concave up for this first section. Positive for this entire section, so this is all concave up. Here, I have a flip from positive to negative second derivative. So for this little section, we're concave down. And then we go back to concave up at the end because the second derivative is positive. Now the last little bit is points of inflection. So anytime that the second derivative touches the horizontal axis, you have a point of inflection. So there's an inflection point at this location, and there's an inflection point right here, and then one final one over here. So to sketch our function, we're going to start with our 3 points. So we have f of -1 is equal to -2. So -1 is equal to -2. We have f of 0 is 0, and f of 2 is +5. So we're looking at the blue now. So our 3 points, we're going to start all the way at the left. So our slope is negative, but we are concave up. So we start going decreasing, concave up, and then 0 slope at this point. Then we are increasing, we have a positive slope and concave up all the way to here. And then we have still a positive slope and concave up. So we're just going to continue this. And then we have a point of inflection over here somewhere. And we flip from being increasing and concave up to increasing and being concave down. So we start to go over through like this. And finally, we are concave up and increasing to the end. So here's my point of inflection. This is my graph for number 2. So for number 3, we're trying to decide which of these 3 graphs is a function and then which are its first and second derivatives. So I'm going to start by assuming, one of these is the function. So I'm going to start with s of x. And so I'm going to say, all right, or the reason I'm making that assumption is because I'm just going to look at this and say, oh, okay, well, there's 3 bumps to it, and everything else has fewer almost. Or I could just start with one. It doesn't really matter. Remember, you can choose any single one of them to start. So I'm going to start by looking at the slope of s of x. So at this location, I could have a horizontal tangent line, so that my slope is 0. Here, again, horizontal tangent line, so my slope is 0. And over here, horizontal tangent line, so my slope is 0. Then, looking at each little interval, I have a positive slope, negative slope, positive slope, and negative slope. So all I need to do is this, and then I can see, okay, well, which of these other functions, if any, matches the values corresponding to the slope of s of x. So if I look at this, the only other function that has a 0 value at this location is the blue function. And it happens to have 0 values everywhere that the slope of s of x is 0. Similarly, it is positive when the slope of s of x is positive, and negative when the slope of s of x is negative. Therefore, it appears that d of x is equal to s prime of x, or you could say ds dx. So now I'm going to continue from this point and say, all right, slope of d of x. What does that look like? Well, I'm going to look for tangent lines where they're horizontal. So right here, I have a 0 slope. Here, I also have a 0 slope. And then I have negative slope, positive slope, and negative slope. And now I'm going to see, does this purple match these values? So it seems like the purple function does have 0 values at the same times slope of d of x is 0. And it seems to also be negative value while d of x has negative slope, and positive value while d of x has positive slope. Therefore, I can pretty much go ahead and get to the end and say that s of x is the function, d of x is, actually we can do this, we can say d of x is ds of x dx, and v of x is either the derivative of the d of x function, or you can say the second derivative of s of x. Either is fine. So questions 4 through 8 focus on this graph here. This graph is given to be a graph of f prime of x. So this is the derivative of some function. So what does this graph tell us? Well, to begin with, it asks where does the graph of our function, so this is f of x, not f prime of x, have a horizontal tangent line? Well, a horizontal tangent line exists whenever f of x has a slope of 0. So when is the slope equal to 0? So this is the same as the times when f prime of x are equal to 0. So in my graph up here, I see 3 locations where that happens. So I have at x equals -2, x equals +2, and x equals 3, f prime of x equals 0. So therefore, these are the locations when f of x has a horizontal tangent line. Now question 5 asks, where does the function have a local maximum, and what is that maximum? So when will it have a local maximum? So if I'm looking at f of x, actually let's use blue. If I'm looking at f of x and it has a local maximum, that would be whenever I have some kind of parabolic or curved shape and there is a maximum value. So as I go toward this, my slope is positive. So this would be a case where f prime of x is positive. Then as I move away from it, this would have to be a case where my slope is negative, or f prime of x is less than 0. So in order to find a local maximum, I just need to find a location or locations where f prime of x goes from positive to negative. So where does this occur? So if I go and look at my graph, I see that my derivative, my f prime of x, goes from negative to positive here at negative 2. Then it's positive, and then at x equals 2, it goes from positive to negative. So this is what I'm looking for. So at x equals 2, f prime of x goes from positive to negative. So this must be, so f of x will have a local maximum at that location. So the question that says, what is that maximum, is a little more difficult to actually answer. So we can't really answer what the maximum is because we don't have any initial values. So let's worry about this, what is that maximum question, at another point in time. So question 6 says, where does f of x have a local minimum? So similar to what we just said above, we're going to use this color. So f of x, we have a local minimum occurring at a location that looks like this. So going toward the local minimum, I have a case where my slope is negative. So f prime of x is negative. And moving away from it, I have a case where my slope is positive. So f prime of x is positive, is greater than 0. So where in my graph do I have a situation where the derivative goes from negative to positive? So in my graph, I see that at x equals 2, my derivative value goes from a negative value to a positive value. So at x equals 2 is negative 2 is one such location. But we actually also have an additional point where it goes from a negative value to a positive value, and that is at x equals 3. So at x equals 2 and x equals 3, my f prime of x goes from negative to positive. So my f of x has a local minimum at that location. And so it's negative 2 and 3. Now, 7 and 8 ask when is it concave up and when is it concave down. So in order to figure that out, I need to go and think about how this is changing over time. So for this entire section to the left here, the value of my f prime is increasing. What does that mean? Well, that means the slope of this section is increasing. Well, the slope of f prime of x, so if I look at d dx of f prime of x, what this translates to is the second derivative. So if I'm looking at the slope here, since f prime of x is increasing, that means that f double prime of x is positive, or this is concave up. For this next section, I have a negative slope. So that means that my second derivative is negative, or I am concave down. For this next section, I have again a positive slope, so f double prime is positive, and my function is concave up. So this is down, up. Here, for this next section, I have a second derivative that is negative, so I'm concave down. And then for this last section, f double prime is positive, so that's concave up. So again, all I'm doing is I'm looking at the slope of my f prime graph. If it's positive, that means my second derivative is positive, and my original function is concave up. So when is my function concave up? It's concave up for negative infinity to negative 1.5. So keep in mind we're given some points here. So f of x is concave up for x values, and we'll say negative infinity to negative 1.5, union 0 to positive 1.2, union 2.6 to positive infinity. And the justification here is because f prime of x has positive slope. Positive slope during those intervals. And so when is it concave down? Well, f of x is concave down for x values. So it's actually going to be every other interval. So we'll just say negative 1.5 to 0, union 1.2 to 2.6. And why is that? That's because f prime of x has negative slope for those intervals. And that's questions 4 through 8. For questions 9 and 10, we have a couple of clues, and we are to decide which is the function and which is the derivative of that function. So for number 9, we're told that when s of x increases, that means that f of x is greater than or equal to 0. And when s of x decreases, then f of x is less than or equal to 0. So what does that tell us? Well, that tells us that s of x must be related to f of x in some way that s of x increasing leads to or comes from f of x being greater than or equal to 0. So when would this be the case? Well, we know that if a derivative is positive, my function is increasing. So that must tell us then that s of x is our function and f of x is some kind of derivative of that function. For question number 10, we're told when t of x increases, k is concave up, and when t of x decreases, k is concave down. So what does this tell us? Well, we have to go a little bit further here. So we know that something is concave if the second derivative, so k double prime of x, is greater than 0. Well, t of x, it doesn't say is positive, it just says it's increasing. Well, we can actually take this back a little further. Well, when would k double prime of x be positive? If t of x were the derivative and its slope were positive. Then we would say, oh, okay, that would mean that t of x is the derivative of k of x. So when this slope is positive, the function would be concave up. So therefore, k of x is the function, and t of x is the derivative. So these two questions were meant to have you really think about how these derivatives are linked together and what they mean from one to the next. So if I know something about concavity, that tells me that the derivative of the function is increasing for that section if it's concave up, or it's decreasing for that section if it's concave down. So I need to be able to use all of these to interrelate derivatives and functions. So for questions 11 through 14, we're given a graph of f double prime of x. So this is the second derivative of a function. So this right here is f double prime of x. and we are asked questions about the first derivative. So in order to understand how this works, we simply need to know how all three things are related. So if I take a derivative of f of x, so if I have df dx, that's going to give me f prime of x. If I'm talking about d squared f dx squared, so the second derivative of f, that is equal to taking the derivative, or the slope, of f prime of x. So what does that mean? Second derivative is the slope of f prime of x. So when would something have a local maximum? Well, just like the problems we did earlier in this homework, f prime of x will have a maximum when the slope goes from positive to negative, right? So we have this thing going on. We have a positive slope and then a negative slope. And this right here is our maximum. So we're increasing and then we're decreasing. So when f double prime of x goes from positive to negative, that's when we have a local maximum. So when is that? We have local maximums going to be at, so this is our positive, or this is negative going to positive, so that's not a local maximum at x equals 2. And then here we have positive to negative at x equals 1. So therefore, at x equals 1, f prime of x has a local maximum. Again, the reason I know this is true is because f double prime of x is just the slope of f prime of x. And when the slope goes from positive to negative for a function, that's when a local maximum occurs. Similarly, f prime of x has a local minimum when the opposite is true. So that's when f double prime of x goes from negative to positive. Right? So this would be the case when we have a valley. So we're decreasing and then we're increasing. So at x equals negative 2 and x equals 3, f prime of x must have a local maximum, or minimum. Because in my graph, that is when f double prime of x goes from negative value to positive value, or negative value and positive value. Question 13 asks us, when is the function, not the derivative, concave up or concave down? So f of x is concave up when its second derivative is positive. So when is our second derivative positive? Well, it is positive from negative 2 to 1, and then from 3 to positive infinity. So it's concave up for x values from negative 2 to 1, union 3 to positive infinity. And it's concave down when f double prime of x is negative. So that's for all other values, not including those zeros. So we're going to be concave down for x values from negative infinity to negative 2, from 1 to 3. So again, this is just talking about how one derivative is related to another or to an original function. For numbers 15 through 17, we are now using physics. So let's go ahead and do a quick run through of what is going on. So s of t is position as a function of time. Then velocity, so this would be v of t, is actually equal to the first derivative so s prime of t. And this is the rate of change of velocity, or just the first derivative of position with respect to time. So this is rate of change of position. Then finally, acceleration is the first derivative of velocity, or the second derivative of position with respect to time. So this is the rate of change of velocity, or you can think of it as concavity of s of t. So both of those are correct. You can also think of velocity as the slope of s of t, since it is the derivative. So for question number 15, we're going to estimate the position at t equals 9.34. So in order to do that, we're going to use a tangent line approximation. So my tangent line approximation formula is f of x is approximately f of a plus f prime of a times the difference between x and a. So in this case, a is some reference value, and x is the value I want to know. So I'm going to use a as 9 seconds, because that is the value I know the derivatives for, and x will be my 9.34. So estimate the position of the object. So I'm not using f, I'm going to switch it back to s because that is position. So s of 9.34 is approximately s of 9 plus, so this is f prime of a, which is the velocity because it is the derivative s prime of 9 times 9.34 minus 9. So I'm going to plug in my values here. S of 9, what position is it at 9 seconds? We know that to be 4 feet. Then we know s prime of 9, because we know the velocity instantaneously at t equals 9 is negative 1.2. Then we have 9.34 minus 9, which is just 0.34. So what is the object's position approximately at at 9.34 seconds? Well, get our calculator and we find that the object's position is 3.558, and that's going to be in units of feet. So this is my approximation. Now, 16 says, or asks, is our estimate too large or too small, and why? So if I think about a graph of this function, so here's my position, here is my time, I know a couple things about how this graph will look. Firstly, I know that the slope is negative at 9 seconds. So if I think about, here's my 9-second mark. So this is my 9-second mark. I'm at a position of 4. My slope, because my instantaneous velocity is negative, also must be negative. And then its acceleration is positive. So s double prime of t, of 9, is positive. So I have a negative slope, so I'm going down, but I have a positive second derivative, so I'm concave up. So this section looks something like this. Now, my tangent line approximation is going to be tangent to this. So at 9.34, I'm going to have a value that is lower than my original function itself. So, is my estimate going to be too large or too small? Well, since this right here is my approximation, and it's below the actual function s of t, that means that my approximation is going to be too small. Why? Because my function s of t is concave up and decreasing near t equals 9. Finally, 17 asks us to describe the behavior of the moving object at t equals 9 seconds. Is it moving toward the origin or away from the origin? So let's rehash everything that we have. So we have s of 9, so the position is 4 feet. The velocity at 9, or the derivative of position with respect to time, is negative 1.2 feet per second. And finally, the acceleration at 9, or the second derivative, actually, we're going to go do both here, or the derivative of velocity, so it's the rate of change of velocity, is equal to the second derivative of position is positive 0.08, and that's feet per second, or feet per second squared. And so what does all of this mean? Well, it seems to be to the right of the origin because it's positive in position. It's moving toward the origin because it is got a negative velocity. And its acceleration is positive, meaning our velocity is becoming more and more positive over time. So this right here tells us object is moving because because we know the object is to the right of the origin, because our velocity is negative, and then our velocity is technically increasing because acceleration is positive. All right, so for questions 18 and 19, we're given a table with the number of Facebook subscribers in millions of people worldwide at 3-month intervals. So each of these represents 3 months passing. So calculate the average change of number of subscribers per month. So this is per month for the time interval shown between March 2001 and March 2012. So I'm going to do each of these in its own color. So for the first interval, the average rate of change is going to be the change in n over the change in time. So my change in n will be 710.7 minus 664. You can say 0.0 if you like. And the time that passes is 3 months. So going into my calculator, I find that this first rate of change is positive 15.57, and this is going to be millions of subscribers per month. So now I'll go on and do this for the rest of them. So for number 2, my average rate of change will be exactly the same. So it'll be delta n over delta t, and that's going to be 756.9 minus 710.7, because that's the previous value, over 3 months. And my calculator tells me that this average rate of change will be positive 15.4. And I'm going to leave the units off because all of the units will end up being the same. So number 3 we'll say delta n over delta t, same method, is going to be 799.1 minus 756.9 all over 3. And this rate of change is 14.07. And then finally, our final average rate of change is going to be, again, delta n over delta t. It's going to be 835.5 minus 799.1 over 3 months. So my calculator tells me my average rate of change is 12.1. So what can we say about the sign of the second derivative during this period? Well, because So because I see that the average rate of change is decreasing, that means my slope is technically becoming less steep. So I'm thinking that if I were to plot these things, it would look something like this. I would have some axes, and my slope would be positive, positive, but it's becoming less positive. So because the average rate of change is decreasing over time, that means that my second derivative must be negative. And similarly, I can think that since I sketched it like this, I can say that it's concave down, which also translates to a negative second derivative. So our question number 20 has a discussion about a plan to replenish the ozone layer. And the ozone layer is measured by something called the ozone depleting gas index. So what we're going to say is that since O of t is our index here, and we know values about the point 2000, we are going to use this O of t function to estimate when the ozone hole will recover. So how do we do this? Well, we're going to use our tangent line approximation method. And the reason I know to do that is because I'm given some values of my function and some values of the derivative. So what does this look like? Well, originally it is f of x is approximately equal to f of a plus f prime of a times x minus a. So what I'm going to do is I'm going to rewrite this for my function o. So o of x is approximately equal to o of a plus o prime of a times x minus a. So what we want to do is we want to say, okay, when will this recover? So we want to know that time when O of x is equal to 0. So my x value is unknown in this case. I don't know how long, I'm sorry, this should be t, not x. We're going to say t and not x. So when is this t going to give us an O of t equal to 0? So in order to do that, we're going to use our a value that is 2000. This is our reference value. So when is O of t equal to 0? So we're going to set O of t equal to 0. O of a, so this is going to be O of, actually let's do this. So O of t is equal to O of 2000 plus O prime of 2000 times some t minus 2000. So we're looking for t in this case. And O of t is equal to 0. So 0 will be equal to O of 2000, which is 95. Our O prime of 2000 is negative 1.25. times t minus 2000. So at this point, it just becomes an algebra problem. So what I can do is I can, I'll do it this way. Instead of distributing, I'm going to move this whole thing to the left side. So I'll have positive 1.25 times t minus 2000 is equal to 95. Then I'll divide both sides by 1.25. So I have t minus 2000 is equal to 76. And then finally, solving for t, I would just add 2000s to both sides, which is 2076. So according to this model, the ozone will recover in 2076.